Everyone. So we're in section 7.2, and for the AB class, we only need to know half of the content that's in section 7.2 from our textbook. And the half that we need to understand are the slope fields, also known as direction fields. And as I talked about in section 7.1, slope fields give us a way of identifying qualities of the solution curves to a differential equation based on properties from the differential equation itself. And so this is a little awkward to do via video. Typically, I would have handouts for my students to work with, and you'd have on your handout graphs like this with some points highlighted. These are called the lattice points. The lattice points are points that have integer coefficients. And we'd be using this to draw the slope fields on and solution curves through the slope fields. But since I'm doing this via video right now, the best thing for you to do would be to get a sheet of graph paper and to set up your XY axes. And whether or not you actually plot all of these points is not that important. But you could, if you're on graph paper, you could see all of these points because you can see all the intersections of the grid lines, and you can still sketch slope fields with me as you go through this. So that's what I recommend, that you take out a sheet of paper and go through this process with me so that you get the experience of creating these slope fields. In past AP exams, there are times when the students are asked to create slope fields and draw solution curves in those slope fields. And so this practice is valuable to you, and it's something that you should work on. Okay. All right, so let's get into this a little bit here. I'm going to start with a really benign example, meaning, or simple example, if you will. Let's get a differential equation here, really simple. Dy over dx is equal to x plus 1. Now, this is one where, even though at this point we technically haven't learned how to solve a differential equation yet, other than taking antiderivatives, you could solve this just by taking antiderivatives. So it would be a rather simple thing for you to do. But the point of this exercise here is to understand how we create slope fields. And I'm using a simple example to do that. So I don't want to solve it, at least not at the moment. We will later, so we can match up the solution with what we see from the slope field and the solution curves that we end up graphing. But right now the point is to understand solution curves. So that's what we're going to be working on. So to do that, let's remember what the derivative tells us about the graph of the function. All right, so let's keep in mind, we're trying to use the slope field. We're trying to use the differential equation to understand properties of the solution curve, the function y that makes this equation true. And we're going to use the slope field to try to get those properties and qualities visualized for us, okay? So if we remember what a derivative tells us about a graph of a function, it tells us the slope of the tangent line at a point. So if I have the point at which I'm looking to find the slope of the tangent line, the derivative will tell me what that slope is. So for instance, this differential equation says that dy over dx is equal to x plus 1. So let's suppose for a moment I'm looking at the point 2 comma 3. Is that on my graph here? 2 comma 3 is on my graph. Okay. So if I'm looking at the point of 2 comma 3, well, what's the slope of the tangent line at the point 2 comma 3? Well, it says, according to the differential equation, that dy over dx is equal to x plus 1. And if x is 2, then the slope is going to be 2 plus 1, which is going to be equal to 3. So what a slope field does is it takes that value and it plots a little line segment in the xy plane with that value so that we can see what the behavior is at that point, if the graph happened to go through that point. So what I would do here is I'd go over to the graph and I'd look at the point where 2 comma 3, this point right over here, and I would draw a little line segment that's got a slope of 3. So, up 3 over 1 or down 3 over 1 in this direction here, and it would be real steep. I'm not going to draw it very exactly here, but it would look something like this. Let me do this so I can get it actually in on the point a little bit better. But it would be a steep line, something like this. It's a short little line segment that represents the slope at that point. Let's look at another point. Let's say we were at the point 3 comma negative 1. Well, what's the slope at 3 comma negative 1? Well, again, it's the x coordinate plus 1 because it says in the diff EQ x plus 1. So the x coordinate is 3, 3 plus 1 is 4. And so when we look at the point 3, negative 1 right over here, that means I got to have a slope of 4. So I'm going to sketch a slope, if I started here at 1, 2, 3, 4 over 1 and connected from this point to this point a line and then just made it shorter, then I would have the slope of the line. Actually, I wanted to do that in red. Okay, so again, I'm lining up these 2 points here, and I'm trying to draw a little line segment that has that slope. And then we would continue doing this at all the points asked for in the problem, okay, which is all these lattice points here. And I'm not actually going to do every single point right now, but it might be a little bit more efficient if we were to make a table. And if we put the x, the y, and then dy over dx over here in the third column, we could come up with some answers pretty quickly. And in fact, there's a pattern in this one that would help us fill this out a lot more quickly than doing these calculations at every single step. Let's start with something simple. Let's start at the origin. If I'm at 0, 0, then to get the slope at 0, 0, I'm going to, again, take the x coordinate and add 1 to it. So 0 plus 1 is 1. And so at the origin, we're going to have 1 as the slope. So it would be something like this. There's my little line segment. But notice something else here. If I keep the x coordinate 0 and go to a different y coordinate, they still get the same slope because the y coordinate is not a term in the differential equation, in this particular differential equation. It will be in others, but not in this one. So as long as the x coordinate stays the same, then the slope is going to remain the same. So if I go over here to 0, 1, then I get another slope that's a little line segment that's parallel to the first one. And that's true if I just keep going up along this direction here, because they all have the same x coordinate, and that x coordinate is 0, and 0 plus 1 is 1, so they all have a slope of 1. And in this example here, because there is no term, there's no y term in it, all points with the same x coordinate will have the same slope. So for this one over here, I could draw in a bunch of parallel, real steep line segments through here. That one isn't steep enough. This one isn't very good. So I don't really like that one. These things can be challenging to draw, especially freehand without lining things up. So you just kind of got to be careful. I don't even think this one here is steep enough that I did way back over here compared if I'm looking at my slopes of 3, but nonetheless, put a bunch of steep slopes over here like this. Try to hit the points unlike that one. And we can keep going. So let's go to a different x coordinate. So if I did the x coordinate of negative 1, and it doesn't really matter what the y coordinate is because the y coordinate, again, is not a factor in this. So what negative 1 plus 1 is 0. So when the y coordinate is, when the x coordinate is negative 1, then we have horizontal line segments here that we would draw in for the slope field. So it's a slope field. It's a collection of line segments that indicate the slope of the tangent line to the solution curve at the point where that little line segment is drawn. Now, for our purposes, we tend to draw these at the lattice points, points with integer coefficients, but they don't have to be. You could pick any point in the plane you want. But on the AP exam, they'll have you do this at specific points, typically with integer coordinates. So let's go over here at -2 for just a moment. At x equals -2, the y coordinate doesn't matter, so I get a slope of -1. So then over here, these are all going to be slopes, sloping down like this. I just realized a major mistake. I hope some of you caught this, all of you caught this. I'm not even going to restart my video. All of these were wrong. Well, why are these slopes all positive? Because I did 3, -1, um, but I went over here to -3, -1, and so I had one thing in my mind and another thing on the screen, and so way over here, these things should have a slope of 4. So I'm going to leave that mistake in there. You guys got to know that I'm human too, and so there's that. Let me go back and finish these. I don't like that one. So like this. And then if I go over here with a slope of -3, then this is going to be -2. So a little steeper than the ones over here, like this. And then if we're over here with an x-coordinate of 1, then 1 plus 1 is 2. And so these are going to be a little steeper than the 1s, not quite as steep as the 3s. Like something like that. Those are sufficient approximations for what's going on here. So that's our slope field for dy over x is equal to x plus 1. Now, I would like you kind of to look at the whole field in total and see what you see there. By looking at the shapes of these segments, of these the slopes of these tangent line segments, you should be able to see the behavior of the curve, and something should make some sense here. Let's use one of these weird fancy colors here. If I was to start at a point like right here, okay, I'm over here in the column where the x equals -3, if you can't see where you put that, and y is equal to about -1.5. I want to draw what a solution curve would look like that would hit that point, okay? Now, remember, when we take and solve for an antiderivative, we end up with a family of curves. So we have an infinite number of curves that would populate this plane that would be a solution to this differential equation, but I want the curve, the one member of the family that hits this point that I just put over here. Now, I'm going to try to sketch it, and I should be able to based on what I see in the slope field, because the slope field tells me the direction of the curve at the point of tangency. That's why it's also called the direction field. And I'm not playing like an old, if you ever had when you were a kid, a little dot to dot uh, exercise where the number of dots, you connect them and it'd make a picture. That's not what we're doing here. I'm not just connecting these line segments. The line segments just give me a direction, a flow of how the curve would populate around there. Okay. I didn't actually calculate the slope at this point, but remember, for a certain x coordinate, the slopes are all the same for this particular example. So my graph would start going down like this. And then, again, I'm not going dot to dot. I'm just trying to follow these uh, tangent lines here with the same shape. When I get to -1, it's got to be horizontal. And then after -1, it's got to start going positive again. Okay, let me actually back up just a little bit. And then it's going to start going positive. I don't like the way. I'm not the best at drawing these things because I'm not a very good artist, but that's okay. And goes something like this and keeps getting steeper again. Something like that. Not very good. I'm trying to be a little too careful. But hopefully that looks something like a parabola to you. And wherever we draw a solution curve through here, I'm going to try to be less careful. It's going to be parabolic because the antiderivative of a linear function is going to be a parabola. And so the set of solution curves here is the set of parabolas that would go, well, I'll get to that in just a moment. Okay. In fact, let me show you a different view of this. This was a computer generated version of the slope field. So it's a little more precise than mine, of course. And again, if I was to draw in a solution curve, trying to be a little bit careful, it would look something like this. Okay, might be a little bit better parabola. The vertex is a little bit off. All right, so dy over dx is equal to x plus 1. I guess I'm using this marker. It's driving me nuts. All right, now I want to integrate that so I can figure out the antiderivative. I'm going to integrate that with respect to x. So I'm going to integrate this side with respect to x. Over here, these end up canceling. We're going to end up with just y. Over here, we're going to get 1/2 x squared plus x plus a constant. And we got it. We got a parabola that matches the shape of the solution curves that we want here. In fact, if we take a look for just a moment, if I factor out an x, no, I don't want to factor out an x over there because it depends on what c is on certain things. But nonetheless, I get a parabola that has its vertex at x equals -1. It's hard to see that perhaps, and this is a good little trick that you probably haven't seen in a while in algebra. To find the x coordinate of the vertex, then what you do is you take -b over 2a, where a is the coefficient of the x squared, b is the coefficient of the x term, and c is your constant in the a, b, and c denotion. So b is 1 here, so -1 over 2 times a. 2 times 1/2 is just 1, so this is just -1 over 1, or just -1. So the x-coordinate of the vertex for this parabola is going to be at -1. The y-coordinate all depends on what the value of c is, but uh, nonetheless, we did see that in the picture, and hopefully you're understanding a little bit better what you're looking at. So let me summarize, and then we'll have to work on more examples. A slope field is a collection of short little line segments that give us the slope of the tangent line to the solution curve at the point where that little line segment is drawn. And it's used to visualize qualities of the solution curve. Now, oftentimes we're doing slope fields on differential equations that we cannot solve. And so, because if we can solve it, then I can just go look at the solution curve and not worry about looking at the slope field um, to get those qualities. I can just look at the function itself to get those qualities. But nonetheless, so we're in general, we're trying to figure out from the slope field qualities of the graph. So, for instance, we're looking at the region over here. We got all these slopes that are negative, and since the slopes are negative, the solution curve would have to be decreasing over there, and it is. Okay, as you can see, if I look over here at all these slopes over here, these slopes are all positive. So that means the solution curve would have to be increasing on that region. Okay, and it is. Okay. And if I look just in general, from left to right, the slopes are increasing. It starts off over here at -2, and then it moves over to -1, then it's 0, 1, 2, 3, 4. So since the slopes are increasing, that means the second derivative is positive, which means the solution curve is going to be concave up. And it is. But we can see that from analyzing the features of the slope field that are going to tell us things about the set of solution curves. All right, so I'm in the software that I used to generate those pictures that I was drawing on a moment ago, because the software itself will draw solution curves to these differential equations for me. The software is called WinPlot, and it's free. It's a little bit cumbersome to use at times. It's actually really, really nice software, but it's a little old school in some of the way things are set up, so maybe it doesn't look as fancy as other graphers and whatnot, but it's really powerful stuff. So anyways, let's say I wanted to start the solution curve up here. There's what the solution curve would look like. So tap it up here. Wherever I tap, it's going to start the solution curve and follow the slope fields. Now remember, oh, by the way, the slope field is generated by the software didn't hit all my lattice points because I can't figure out, I'm not sure if it will, how to tell it just to hit the lattice points. So it sets it up in its own default way where it's going to give you a whole bunch of line segments. I can control some features of how many line segments, but I couldn't figure out how to tell it just to do it at the lattice points. So it doesn't matter. So remember I said the line segments could be drawn anywhere in the plane. We just tend to have you do it at the lattice points for ease. So nonetheless, these are just spread out throughout the XY plane and not at the lattice points. So wherever I tap, you can see that we get all these family of parabolas, all with a vertex at x equals -1, that are solution curves for that differential equation. All right, I'm going to make another video for more of this topic. So that'll be your first part.